Okay, welcome everybody to the Budapest Summer School in Graphs, Groups and Stochastic Processes. This summer school is organized by the Rényi Institute and ELTE. And if you have any questions, the organizers are myself. My name is Bálint Virág. It's László Lovász over here. Miklós Abért over there in the back. Ágnes. There is Ági Backhaus and Balázs Szegedi also in the back. So if you have any questions, you have a yellow tag, so just come and ask us. We're going to have lunch, and for the lunch you have coupons. The coupons you can find in your packages, and these come for a certain amount of money, and they're like kind of vouchers, so you will know how to use them. And there's going to be a problem session at 4:35, and we thought of this problem session as something in addition to the summer school. If you feel like it's useful for you, come. If you don't think it's going to be useful for you, you don't have to come. So we would like to have a group of active participants. So please decide if you like that or not. There are two things about the Institute that you should know. You see, we're almost up to capacity here, and the restrooms are really small, but there is one on every floor. So there is one outside here, and then there's one on the floor below and the floor above, and even on the 4th floor. So just feel free to look for those. And the other thing is that security is taken kind of seriously here, and that means that at 7 p.m. Everybody has to be out of the building. So please leave before then, and you can come back the next morning at 7 a.m. But after hours, there are all kinds of. The police is going to come if they find people and so on. So, okay, so that's all I wanted to say, and I'll give the word to László Lovász for the first talk.
Okay, so. Welcome here. It's very nice to see all of you here, and I would like to give a kind of introduction to the topic, but I had my notes here, and did somebody... No, yeah, okay, thank you. So I would like to give a little introduction to the topic, and first of all I would like to illustrate the idea of why do you want to go to limits of discrete structures. What is the motivation behind this? So the idea is that suppose you have a very, very large graph. How can you, what information is important about it, and what information is that you can ignore? And if you ignore all the information that you want to ignore, how can you collect or compactly describe the information that you really need? So let's look at a couple of examples. A complete graph is a complete graph. It's a very boring object. That's all. I mean, the only information about it is that any two nodes are adjacent. So that's not very exciting. Now suppose you take a complete bipartite graph. Then all the information about it is that it has two classes, and well, it's not quite true. And then everything between them is adjacent, so more or less you can describe it here. But you also need an additional information about the relative sizes of the two parts. So if one is half that large as the other, then maybe you can put here weights 1/3 and 2/3. So this is all that contains the information. Well, we ignore a lot of information, for example, whether it has an even or odd number of nodes. But we feel that this is irrelevant information if it is very big, and all the information can be collected in this picture. Or suppose you take a random graph where each edge is put in with probability p, say 1/2, specific, a very large number of nodes. Well, it turns out that, as long as the number of nodes is small, this has all sorts of interesting features. With some probability, it will have isolated nodes. It has a certain number of triangles, which is an interesting random variable, and so on. But if it is very large, then all these features will be just subject to the laws of large numbers, and really everything can be compactly described in something like that. So this point represents here a huge number of points, and between any 2 points there is an edge with probability 1/2. Now there are more complicated examples. So suppose you take a graph where the nodes are arranged on a cycle, and any 2 nodes are connected, which are at a distance on the cycle at most n/3. N is always the number of nodes. So this is again a graph. So what is how to collect the information about this graph? Well, as you see, the n doesn't play any role. We don't care. So really, you can sort of think of it as a continuous circle, where 2 points are connected when their distance is less than 1/3 of the, less than or equal to 1/3 of the length of the circumference of the cycle. Let's look at a little bit more complicated example. Suppose we look at a graph where the nodes are labeled 1 through n, and we connect 2 of them, I and j, if the GCD of I and j is 1, if they are relatively prime. Now, that's a complicated graph. There will be nodes which are connected to, say, the node 2 will be connected to half of the other nodes every odd node, but some other node, a prime, is connected to many, but then there will be others which are, a large prime is connected to everything else, a prime which is more than half. So it's a complicated graph, and I'm not going to describe it to you. It can be considered as an exercise to figure out how exactly compactly describe the information in this graph if it's large. But to see, so one question is, so suppose I pick 2 random I and j, will they be connected, or with what probability will they be connected? If this, one danger is that this probability will be so small that if n is large, this basically looks like a graph without edges. But actually, that's not the case. If you do some computation, you can see that the probability that there is a prime p, that a given prime p divides both I and j, well, the probability that it divides I is roughly 1/p, so that it divides both is 1/π². So the probability that this p is not a common divisor is 1 - π². And now I can wave my hands and say that for different primes, this is maybe happens independently. So I can take the product over all primes, and this is a number which is strictly between 0 and 1. So it's an interesting graph, and you can figure out what is the limit if n tends to infinity. So it's how to find a kind of compact description similar to these. So next example, let's take graphs where the nodes are labeled 1 through p minus, or 0 through p minus 1, where p is a prime congruent to 1, 1, 4. And connect two of them, I and j, if I minus j is a square, it's the square of some other, of course, modulo p. So, k squared modulo p, it's congruent to k squared modulo p for some k. So if the difference is a quadratic residue, this is called a Paley graph. It's a very nice symmetric graph, has all sorts of interesting properties. But the question is now, suppose we take P very large, so huge. So what features do we have of this graph? Of course, there are some features, like every node has the same degree, which is it's a very special feature, exactly the same degree, it has a symmetry. But as long as we are concerned only with kind of local properties, it turns out that this is just like a random graph. It's called a quasi-random graph. So if we want to figure out what's the number of triangles here, then asymptotically it will be the same as in this graph. So if they are very large, and we can look at only at locally, and this graph, the random graph, are indistinguishable. They behave exactly in the same way. Now, let's look at a different kind of example. Let's take just a cycle, Cn, a cycle of length n. So what should be the limit of this? Well, one possibility is to think of it as a circle, a continuous circle. But it's not so easy to say what properties of this cycle, graph theoretic properties, are reflected by this circle. It's really not reflected. It has a different structure. The other possible guess is that it's an infinite path. Now that looks better, because at least it reflects the property that if you look at any point and look at the neighborhood of this point, no matter how far you go, if n is large enough, you will see just a path. And this is the same here, except here you, on this single graph, you get this infinite, the arbitrary long path as a neighborhood of a point. It turns out that this is still not the right one, because I mean, this construction lacks one important feature, and this is that if you pick a random point on this cycle, this feature, there's no meaning of picking a random point on this path. Now, of course, you can say, why should I pick a random point if they all look alike? But I will show you an example in a minute which illustrates that this is important. So if I want to construct some limit of a cycle where you can pick a random point, then I sort of have to mix these two ideas. I mean, one example, there are many ways of constructing such thing, but one example is to take a continuous circle and then connect 2 points on it if their distance is some given alpha, which is an irrational multiple of pi. So in other words, if I start and step on the edges here around, then I go never return to the point which I have been to, and of course you can do it backwards. So every connected component of this graph is this path, but we have sort of combined an uncountable number of these paths into a single object, but now we can pick a random point, because you can pick a random point on this circle. So this is one feature of being able to sample, to look at a random example, a random point, and let me show you. It's okay. So first, I need. Screen here. So here is what's called append row styling, so here is what's called append row styling. Probably most of you have met append row styling. So this is consists of two kinds of little rhomboids, and which is not shown here is that. So the question is how to tie the plane with these two rhomboids. Now, what is not shown here, of course, you can tie the plane with a single rhomboid just in a trivial way, but we exclude this. We don't allow a rhomboid to be glued with the same edge on the other side. So there is a rule of how you can glue together two of these rhomboids. So which edge can match which edge, and if you follow this rule, then you get a tiling like this, and this kind of tiling has a very beautiful theory and very interesting properties. So, for example, the whole plane can be tiled, but it cannot be tiled in a periodic way. So, no matter how you tie the plane with these two rhomboids, satisfying these restrictions on how to glue them, there will never be a period of this tiling. Moreover, if you look locally, you see all sorts of different configurations, but there will be configurations which, a configuration, of course, there's a finite number of possible configurations, so the same configuration will be repeated. So, for example, this configuration also occurs there and there in the picture. So, and it turns out that if you count how many times does it occur in an n by n grid, the n tends to infinity. This has a limit. So all of these have densities. Every finite configuration that occurs with a fixed density, independently of which tiling you take. There is an uncountable number of possible tilings, but no matter which configuration you take, it has some kind of fixed density. So what I'm saying is that this is, if you look at larger and larger pieces of this tiling, then in a sense it should have a limit, because the larger and larger, the more exactly the densities of these subsets, these sub-configurations will be given. And so it's a question of what is the limit of this. And Nishibara's figured out what the limit is, and it's here. It's just to show you how complicated but still interesting things can get. So you have to take a special three-dimensional convex polyhedron called the rhombic icosahedron, and all the vertices you see here are the vertices of a rhombic icosahedron, and then slice it parallelly through vertices, and you get two extreme vertices. So slice it into pentagons. So the vertices are arranged in pentagons, 4 pentagons plus 2 extreme vertices. And now the point is that you can, so to describe the limit object, you can take the points on these pentagons and connect 2 of them if the corresponding segment is a translate of one of those 10 that I have drawn there. So really, you take this and you shift it between 2 of these in any possible ways, and then you get an infinite graph with continually many vertices. And then in this graph, if you pick any point and you follow the connected component of that point, you get a Penrose tiling, and then you get all of those. So we take all Penrose tilings and pack them up into this single picture. And then this picture represents, in some sense, the limit of all Penrose tilings. Now, if you think about it, it shows that it's sort of natural that you need continually many points to describe the behavior, because if you take any Penrose tiling at any point and you look at larger and larger neighborhoods of this, eventually if you start anywhere else, you will see something different. So this gives you continually many possible views. And all those views, local views, are combined into this picture. Okay, so actually, this was just to now I will not actually these last couple of examples are a subject which I will not talk about, because these will be graphs with bounded degree. But the only thing I wanted to point out that if you look at this picture, you will think of ergodic theory, and then you will get interested and you will listen to the next talk. Come on. So now let me now come back and try to illustrate. So why consider limits? Here is one more motivation, and I apologize to those who have heard this maybe a dozen times. Let's look at the following question. Let's minimize x cubed minus 6x over x greater equal to 0. So there's some cubic curve, and here is the minimum, and the value is attained at square root of 2 if you do the differentiation. And so that's an easy minimization exercise. But it's only easy because you have real numbers. If you want to solve the same problem in rational numbers, so you're an ancient Greek mathematician and don't believe in irrational numbers, then this does not have a solution, and the correct statement is that you can find numbers which get arbitrarily close to this minimum value, but it never reaches it, and so you cannot really exactly find the minimum. But luckily we have real numbers, and so the minimum is at square root of 2. Now let's look at the following problem. Find the minimum density of 4 cycles in a graph G with edge density 1/2. So suppose exactly half of the edges, possible edges are present, and then you count 4 cycles, and you want to find the minimum. But let's say that we count also degenerate 4 cycles. So by a 4 cycle, I simply mean a path of length 4 which returns to the starting point, and you count these objects. And then there is a theorem. It's not a very hard theorem. Goes back to actually Erdős in the 1950s, which says that this density is strictly larger, in fact, than 1/16. It's always strictly larger than 1/16. But for example, for random graphs, also for Paley graphs, it gets arbitrarily close to this 1/16. So it's a similar situation here, and then you would like to get maybe some kind of graph-like object, just like real numbers are number-like objects, which we add here in order to be able to solve problems like this, that we want to solve problems like this. And this all again motivates the introduction of these limit objects. Now, so I would like to summarize what is known about limit objects in the case of dense graphs. So I consider dense graphs. So that means that a positive fraction of all possible edges is present. And we would like to define a number of notions. We would like to define convergence. So we have a sequence of such graphs. When is it convergent? We'd like to define some kind of distance. We'd like to introduce limit objects. If a sequence is convergent, then how to compactly describe the information that we need about it, and finally something about the space of limit objects. If you think of the case of rational numbers, so suppose you start with rational numbers, you can define convergence in the usual way. Distance is trivial, it's just the absolute value of the difference. The limit objects are the real numbers, and if you are interested in the space of limit objects, you get topological properties of the line. But now what happens with graphs, if you want to do all these steps? So let's start with the definition of convergence. We are interested in the local structure of these graphs. We count all sorts of subgraphs. I mean, the number of edges has already come up several times. So in general, I will define we have G as the homomorphism. I call it the homomorphism density, or just density of F in G. Now, to be precise, one way to define it is the following. Let's map vertex set of. So these are simple graphs. So I will talk about simple graphs today. So let's look at a random map from the vertex set of F to the vertex set of G, and then TFG is the probability that edges are preserved. So that every edge of F is mapped onto an edge of G. So that's how I define this density of 4 cycles, because really a path of length 4, it's really, so in other words, I take 4 points and what's the probability that number 1 is connected to number 2 is connected to number 3, this to number 4, and that back to number 1. So you can of course expect this as, I mean, just, it's, you count the number of homomorphisms of F into G, so this is all maps that preserve edges, adjacency, and you divide it by the total number of maps, the number of nodes F to the number of nodes of G. So this is how I define the density of F in G, and then we can say, okay, and now I look at a sequence of graphs G1, G2, and I will always assume that the number of nodes tends to infinity, so you don't get the same graph infinitely often. So number of nodes tends to infinity. And then we say that this is convergent if for every F, fixed graph F, the density of F in Gn is convergent. It's a numerical seed. Convergent. So this is the basic definition, and so we are interested in characterizing these convergent sequences in various ways, and then we are also interested in assigning limit objects to these convergent sequences. So how to work with that? So the first thing is that we would like to characterize this convergence in terms of some kind of metric. So introduce topology. Now this is trivial, and you can, for example, define the distance of two graphs, G1 and G2, by taking something like the sum of the density of F in G1 minus the density of F in G2, and you have to normalize so that this sum becomes, so you will be summing over all isomorphism types of finite graphs, and here you have to divide with something which makes this sum convergent, say 2 to the number of nodes of F squared. Now this is okay. I mean, this gives you a distance, defines a metric space, a topology, which will exactly correspond to this convergent. But now you feel that this is cheating. It's really just, I mean, I forgot an absolute value. This is clearly cheating because this distance doesn't tell you anything else than this definition. So the question is there a kind of more structural notion of distance? And since this is used in many considerations, I would like to introduce it. The definition will be somewhat hairy, and you have to struggle with it a little bit, but it will be then very useful, and indeed seems to be the right definition. So let's start with two graphs which are defined on the same set. What should we consider as the distance of these two graphs? The most natural notion is what's called the edit distance, where we count how many. I mean, we take the symmetric difference of the two edge sets, and we are just interested in the size of that, maybe normalize if you want. But that would not be, that would be too strong, right, or too weak. So in other words, to be close in that distance is too strong a requirement. So for example, if you take two of these random graphs, so you take fix n, fix the set of vertices, and generate two random graphs with edge probability 1/2. Now, these two random graphs are very similar if n is very large. It's very difficult. If you just begin to look at them, they look alike. Almost every feature that you can think of will be the same for the two. Nevertheless, their distance in this edit distance sense, how many edges you have to change to get from one to the other, is very large. You have to change about half of the edges of one and insert that many edges into the other to get to the other. So this is does not reflect the kind of structural similarity that we are after. And so we actually take a different notion which we call the cut distance. And the cut distance of these two graphs is defined as follows. You take two subsets, and then these will be chosen in a most worst way, S and T, and then you count the number of edges in G1 between S and T, that's how I note it, and count the number of edges in G2 between S and T, take the absolute value, and you divide this by n squared, where n, as always, is the number of nodes. And that's called the cut distance. It's called a cut distance because actually you could take here just a set and its complement, in which case this is just a cut between the two sets, and so we count the number of edges in each cut. You will lose possibly a factor of 2, or maybe even 4 if you do that. So, but it turns out it's more convenient to allow 2 independently chosen sets here. Now, one other question is, if it's again a discussion that you have to hear once, is that it looks more natural to divide here by the product of the sizes of the two sets, because then these numbers are bounded by this product, so you get something which is less than 1. The trouble is that then the maximum will be attained if these are singletons. So it's either if there is any pair where two singletons, where there is an edge here but no edge here, and this quotient is 1. And so it will give too much emphasis to the large sets, so to the small sets. So therefore we divide here by n squared. And so this is called the cut distance. Okay, cut distance is actually a quite interesting distance. There's a lot of solved and unsolved questions about it. But now let's go on. I mean, this is only the case where the two graphs are defined on the same set of points. But now we are talking about two abstract graphs. In fact, we want to define distances between any two of these members of this sequence of graphs where the number of nodes tends to infinity, so they will have in general different number of nodes. Nevertheless, let's start with, let's make as a next step the case when the two graphs have the same number of nodes, denoted by n, but they are not defined. They are defined on two different sets. Well, in that case, of course, what we do is we identify the two underlying sets that we can do in many ways, but of course would like to get the best overlay of the two graphs, so we define the And now I denote it by, instead of D, by a delta, which emphasizes that these are now defined on different sets. And I put here a star because it's still not the final word. But let's define this as the minimum. Well, I will just write it like this: over all identifications of G1 and G2 of the vertex sets of the, and once they are identified, then this cut distance is defined. And but now this doesn't work if the number of nodes is different. And then in this final step, what we do is, well, we have to make the number of nodes the same, which we do by blowing up. So if M is a number, then I denote by, and G is a graph, then I denote by GM the graph which is obtained. So here is some graph G, and GM is defined by replacing each node by M nodes. And if there is an edge between two original nodes, then I put all edges in. If there is no edge, I put no edges. So we call this the blow up, the M blow up. Blow up of G. And then now we can, with this notation, we can now look at the following. We take two graphs now, G1 and G2, arbitrary graphs. The number of nodes in GI should be Ni. And then we can take the following. We take G1 and blow it up, certainly by N2, but actually N2 times some K. So some multiple of N2, and we blow up G2 by some multiple of N1. So these two graphs now have the same number of nodes. So this kind of delta star distance of them is defined. And now I can take the limit of this as k tends to infinity, and this is what I define. This is this cut distance of G1 and G2. Well, that's quite a number of steps to arrive at this distance, and accordingly, it's not a very easy distance to handle. But there are, but it turns out to be the right one, the useful one. Okay, so this is the distance of two of these graphs. It's not hard to see that the distance of two random graphs, as soon as they may have different number of nodes, but these numbers are large, then the distance will tend to 0. So it will be small. Because you take the blow up and then overlay them, and then you have to do a little computation with laws of large numbers to see that between any two sets they still have about the same number of edges, the right number of edges, which is of course half of the total possible number. Now once we have these notions of distance, and even with the relatively simple first notion, it is one can use it to express some other basic results in graph theory. And let me formulate one of these, which is the weak regularity lemma. Now, actually, I need to go back and make things a little bit more general. So, for a convenient formulation, here we have considered simple graphs, but it will be convenient to consider simple graphs where there will be edge weights, so edge ij may be weighted by beta ij, some number beta ij, where I will assume that these are always between 0 and 1. So we can allow edge weights. Now, how do things change? The only thing that changes is when I count edges between two sets, I have to count them with these weights. So instead of adding 1 for an edge, I only add the weight of that edge. And here 2, and then so we can define this distance of 2 weighted graphs, and then the rest goes exactly as before. And so we can define this cut distance of 2 weighted graphs. And then this weak regularity lemma says the following. So, I have no time to talk about the regularity lemma in general, which is a basic tool in graph theory, and probably most of you have met it. The weak regularity lemma, so the original was proved by Semeredi, and the weak version that I am going to formulate is due to Fries and Cannon. And one way to formulate it is the following. So given a graph G and given an integer k, at least 1, there exists a partition of the vertex set of G into k parts. Call this partition P. So P is a partition. So this is a partition. Okay. Now, given this partition, I can define a weighted graph. So here is the graph G, and here is the partition. And now I define another graph which I denote by G sub P. And that's the following. It has the same set of nodes and the same partition. But here there is, well, whatever is bipartite subgraph is here between two partition classes. Here I put a complete bipartite graph, but I weight the edges with the density of this subgraph. So if here half of the edges is present, then I put here a weight of, so the weight of each edge will be the number of edges in G between these partition classes V1, V2, divided by the size of V1 side times the size of V2. So this will be the weight of these edges. And actually, it's convenient to do the same also inside V1. So if there is a certain edge density in this graph, then I put here a complete graph with the appropriate weights on the edges, where the edge density is the weight of the edges. So this is sometimes called a template, or it's not quite a template. A template would be shrink these to single point. Let's just call this G sub P. And so there exists a partition such that if you look at the distance, and these are on the same set, so I don't have to bother about these overlay problems. The distance between these two graphs will be less than or equal to maybe 20 over square root of log k. So in other words, you get this graph, which has a very simple structure. So its structure is completely described by k numbers, which describe the relative sizes of these partition classes, and these beta I, so these edge densities between these classes, edge weights. So this is a very simple structure. It's a large graph, same size as G, but it's a very simple structure. And they are close to each other, measured in this distance. There is an alternate way where instead of putting here edge weights, you could put here a random graph with those edge weights, and then a similar conclusion would hold. So in another formulation, you actually get another simple graph here instead of this GP. So instead of a complete graph with edge weights on the edges, you take a random graph with that density. And that would also work. It's not difficult to see. So this is the weak regularity lemma, and what does it say? It says that if I look at all graphs on a given number on a given set, then in this set, if you look at graphs with this simple structure, then they will be reasonably dense. So there will be a finite number of them, and they will, of course, I mean, everything is finite at this point, but they will be quite densely distributed relative to this distance. So this is the weak regularity lemma, and now the theorem is that a sequence G1, G2, and so on is convergent of simple graphs if and only if it is Cauchy in this cut distance. So this distance, I mean, does the same job as the distance as those trivial distances, but in addition, it's some kind of structural thing. It says if two graphs are close, then they can be, well, blown up and overlaid, so that after that, between any two sets, there is about the same number of edges. So it does give you some kind of structural condition on this, on being close. Convergence. One more remark about convergence, since this probability is in, or some kind of stochastic processes is in the name of this conference. This, to be close in this sense, that the density of graphs is, small subgraphs is close, is equivalent to saying that if you take samples from the two graphs of a given size, that the distribution of the, I mean, if you take a sample, you see a graph on k points. So if you choose k random points from a large graph, then you get a distribution on graphs with k points. And you do the same with the other graph, you get another distribution, and you compare the two distributions, and you will see that these distributions are close. And that's it's not hard to see, because really the fact that we are counting homomorphisms here instead of, we could count subgraphs, or induced subgraphs, and these are just inclusion-exclusion formulas that express one with the other. And if you count induced subgraphs, then and normalize, that's exactly would be the distribution of the samples. So this is the same. You can think of it as a third characterization of convergent sequences, that the sequence is convergent if through sampling, if you look at, for every k, you look at the distribution of subgraphs of size k, induced subgraphs of size k, then these distributions are convergent. Now a few words about limit objects. You have to define, they are called graphons, and the graphon is, well, for today, it's a function defined on the unit square and with values in 0, 1. And it should be symmetric and measurable. Integrable because it's bounded, so it's the same. Symmetric in the two variables, so it's a two-variable function, and it's symmetric in its two variables, and this is called a graphon. We can, if we have a finite graph, then we can think of it as a graphon as follows. So we have here the unit square, where this function should be defined. We divide it into n by n grid, little squares, n squared little squares. And it's like the adjacency matrix, so we put a 1 if the i's in the ith row and the jth column, if nodes I and j are connected in the graph. So far it looks like the adjacency matrix, but we think of this as the value of the function on that square. So this way we assign to every graph G a function W sub G. To be more precise, this depends on how we label the nodes. So to every, with a given labeling of the nodes, we assign a function W sub G. And so this is a special graphon. It's a very special kind of graphon, since of course there's a huge variety of such symmetric measurable functions. And now the main theorem here is that if G1, G2, and so on is convergent, then there exists a graphon W such that, oops, I forgot one definition. You can define the density of a graph F in a graphon W, and that's defined as follows. You will assign a variable to each node of F. So you will have a coordinate or a variable for each node of F. And now you take, for every edge ij of F, you take W evaluated at xi and xj, take the product of all of these, and then you integrate this according to all the variables. So you see that if you think about this particular W, then here this product will be typically 0, except if all of these xi, xj's are fall into the pairs, fall into squares where the value is 1, which means that it only depends. So first of all, this only depends on where the variables xi fall in this partition, And if one variable falls here and the other variable falls here, then the value depends on whether the two corresponding nodes are connected. So basically you count homomorphisms, and since the size of these squares is 1 over n squared, you normalize it. It turns out you normalize it in the right way. So this is 1 over n, so you normalize it by exactly that value. So this can be defined, the density of f in W. And so there exists, so if you have a convergent sequence, there exists a graphon W such that for every f, the density of f in Gn tends to the density of f in W. And so this graphon will be considered as the limit object of the sequence, so we write that sequence Gn tends to this W. Now, there is this W is of course not uniquely determined, because, I mean, for example, if I replace each variable xi by 1 minus xi, then this integral will not change. So, so in fact, I can take, so if here is this function W defined on unit square, I can take any measure preserving transformation and apply it on both coordinates. This will not change these integrals, and therefore I get another W which represents the same thing. There is a theorem about uniqueness, but there are some technical issues here, and since I am out of time, I will not discuss it now. So you have to be careful with formulating the uniqueness, but basically up to this kind of measure preserving transformation in the variables, the W is unique. And okay. Okay. One more definition. You can actually define the cut distance of two W's which is defined as the supremum over it's the exact extension of this. So you take two sets S and T, measurable sets of course, 0, 1, and then you integrate over S cross T W1 minus W2. And this, W1 minus W2, and the absolute value, you can put the absolute value on the outside. But that's now the unlabeled distance, and then you have to define this. This is the labeled distance, and the unlabeled distance, the delta distance, where you have to take as the infimum overall phi, which is a measure preserving transformation, the previous distance of W1, but you transform it by phi and W2. One way to define it, you could put phi on the other one and so on. You can check that this doesn't change the infimum. So there is a distance of these two guys that can be defined. Luckily, the blow up, at least one step out of this, the finite case, this is not needed here. So it's a little bit simpler. So I am out of time, but I said I would like, I need to say, I want to formulate one more statement, and that's the let this script W0 be the set of all graphons. And then we take this W0 with this distance that we defined. Now the problem is that this distance can be 0. For example, it could be that W1 transformed appropriately is exactly equal to W2. So if they are equivalent, they represent the same limit object, then this distance could be 0. So this is just a kind of symmetric space. But the main property of it is compact. And that's actually equivalent to the regularity lemma, which is some kind of nice analytic formulation of the regularity lemma. And in fact, it's sort of not so surprising because the regularity lemma says that there is this simple structure that can be the partition structure. So those graphs with this very simple structure are dense among all graphs, and therefore so there's a finitely compactly described subset which approximates every graph, and the graphs are of course dense in graphon, so they approximate every graphon, and then that's the end of it. I have run out of time, so I will stop here. Thank you. Questions? Yeah. Actually, all versions of the regularity. So the weak regularity implies this, and all other versions can be derived from this, including the very strong versions by Alon and Shapira and others. Okay, this is not quantitative, so the qualitative versions of the regularity lemma, yeah, that's right, yeah. Yes, that's also true if you go to this delta distance instead of the d distance. So, well, you get a graph with k vertices, but now the k vertices have weights, and also the edges have weights. But now you can do some blow up, but of bounded size. So you can blow it up to bounded size and replace it by random graphs, the weighted edges by appropriate random graphs with the appropriate density. And so in fact, it also follows that with respect to this delta distance, this delta distance, graphs of bounded size are dense. You lose in the constant, so but other than that, so every graph, no matter how large, can be approximated by a graph of size roughly of size k with an error of maybe 40 over square root of log k. That's not hard to see, but you have to prove it, yeah. It's not, we have to work a little bit. Sorry? Oh, no, they are not necessarily disjoint. So you can You can choose, you can impose various properties here. You can even take S equals T, or you can take S T to be the complement of S, or you can require that they are disjoint. And they all give the same value up to some absolute constant like 4. So, just a technicality. Yes and no. Yes, basically there is a limit theory of hypergraphs, which was worked out by Gábor Elek and Balázs Szegedi. You get regularity lemmas for hypergraphs. That was proved earlier by Rödl, Gowers, Koch, and others. And then there is also, for example, this kind of distance which would fit very well is not there. So that seems to be missing. That's a good question. No, there are. I mean, this is an infinite dimensional space, but it. Yeah, no, I don't know anything. I mean, in certain finite projections, which are combinatorially interesting, are known. But even there, some topological properties are not known. So, for example, you can take this space and then these density functions, and then you can ask what is the range if you pick, say, the adjacent triangles. So that's a projection of this topological space. That happens to be simply connected and everything, but I don't even know whether it's always simply connected if you take a finite number of these projections. So it's probably it may be that there is something there, but I don't know. It's connected. That these sort of things are not pursued. Thank you. I think it's coffee break now.